Okay, adding and subtracting complex numbers. This is super short. It is super easy. All you ever have to do when you're adding or subtracting complex numbers is just treat the I like a variable. That's it, right? That's it, no problem. So for example, when I'm adding them, I don't even really need those parentheses there, right? The parentheses aren't doing anything. Parentheses are only useful when we're distributing something or we're taking something to a power, for example. But we're not doing anything to either one of those groupings. The only reason they're there is visually so we can realize that we've got one complex number plus another complex number, right? But if those were x's, what would you get? I mean, if you had negative 11 plus 3x plus 9 plus 2x, how would you do that? How would you simplify that? What would you do, Elijah? Say it again. Yeah, just combining like terms, wouldn't you? You'd combine the constants and the x terms. Well, just treat the i's like x's. So what do we get then? If we add up the constants, what's negative 11 plus 9? Negative 2 plus 3i plus 2i. That's it. It's that simple. Piece of cake. So if you're subtracting, let's jump down and look at number 4. I'm just going to look at a couple examples. You guys don't need to go through a lot of these. So if I'm subtracting, the only difference is rather than trying to distribute in your head and keep track of all that stuff, it's much easier just to distribute the negative and add, right? So we'll rewrite this as 6i. If I distribute the negative, would you guys agree I'm going to get a minus 14 plus I, because I'm subtracting a negative, plus 5 minus 3i, and now I just combine like terms. So again, if I'm just combining all the constants, negative 14 plus 5, what is that, negative 9? And if I combine all the imaginary terms, 6i plus I is 7i minus 3i is 4i. Make sense? Piece of cake, okay? Could not be easier. I mean, that's no big deal. So when we're multiplying complex numbers, you do almost the same thing. We're still just going to treat the I like a variable and just distribute like normal. Okay, so let's look, for example, at, tell you what, let's do number 5. In addition to the ones I've got highlighted up there, let's do number 5 also. So if I distribute the 2i, what am I going to get there if I distribute that 2i, Jack? Okay, so I'm going to get 16i minus 6i squared. But what's I squared equal to? Negative 1. So the only difference here when we're multiplying complex numbers, we're going to treat the i's like a variable, but we're going to recall that I squared is equal to negative 1. So every time we get an I squared, we immediately convert that into a negative 1, right? So what's that going to do to this second term? If I take that I squared and it becomes a negative 1, what does that do to the sign of the second term? It just makes it positive, and then I'll just convert the I squared to a negative, which means I cross the I squared out, and then I just change the sign of the term. So would everybody agree? Then I end up, if I want to write my answer in standard form, it wants me to write these complex numbers in standard form. We always put the real part first. So I've just got 6 plus 16i. Everybody agree? All right. What about number 8? Okay, if we look at number 8, this is just regular, we're just distributing here, right? Like you guys used to call it FOIL probably, right? I'm not going to call it FOIL because when we get to polynomials, which we're probably not going to get to this year, but when we would have normally in a normal year gotten to polynomials, which you'll do at the beginning of next year, when you distribute, you don't FOIL because sometimes you have more than 2 terms in each polynomial. So we want to get used to the idea of just distributing. So we're going to take the first 2 terms and we're going to distribute those over the second 2. So when I distribute the 2, I'm going to get negative 10 minus 6i, correct? Okay, when I distribute the negative 4, negative 4i, sorry, negative 4i times negative 5. Everybody agree that's plus 20i. And then finally, negative 4i times negative 3i is positive 12i squared. And what's the I squared do? Changes the sign, right? The I squared changes that to a negative. Okay, so now all I've got to do is combine like terms, and I'm done. Negative 10 and negative 12 is negative 22. Negative 6i plus 20i is plus 14i. Okay, good. Well, number 9, I mean, we don't even really have to do number 9 because it's the same problem. It's the same kind of problem. 6 minus 2i squared, I can just rewrite that as 6 minus 2i times 6 minus 2i and FOIL it out, or distribute, just like we did on the last one. Okay? So what if we have something complicated like this? We just follow order of operations, right? Order of operations work for all numbers, including complex numbers. So if I want to simplify this expression, what am I going to do first? Okay, meaning multiply, right? Because I've got a complex number times a complex number, so that's multiplication. So the first thing we're going to do is take care of that product, right? We got to FOIL all that stuff out. So if we do that, let's see if we can keep track here. If I distribute the 1, you guys tell me, what am I going to get here? Read off the terms to me. 9 plus 3i good plus 63i. Okay, good. 21i squared. And we could maybe even just write that immediately as what, Elijah? 21i squared is going to be? There you go. Make it a negative 21. Okay, and so then all that stuff right there, we could add up the like terms. And then on this other part, I'm just going to distribute the negative, aren't I? So I'm just going to get all that stuff minus 4 minus 2i. So let's just combine all the like terms then. So let's see, we've got the constants, the real numbers. I've got 9, negative 21, and negative 4. We're going to add all those up. So that gives me negative 25 plus 9, negative 16. Good, okay. Let's see, how about all of the imaginary terms? So 3i plus 63i is 66i minus 2i, 64i. Done. Piece of cake. Okay. All right. Okay, so I want to look at real quick one other topic here, and then I'm going to let you guys work on this stuff. And really, this gets us all the way through the second assignment. So I want you to notice what happens when we multiply together two complex conjugates. And conjugates, remember, I mentioned conjugates earlier in the year. You may not remember what conjugates are. So let me just remind you about conjugates. So conjugates are terms that have this kind of a pattern. Whoops, that's supposed to be an A. Conjugate expressions. Or just conjugates. We just call them conjugates. Look like this. A plus or minus B. So in other words, A plus B and A minus B. So I've got this first term and this second term that are being added in one case and being subtracted in another case. And together, those are called conjugates. Okay? You might remember this because we had a factoring pattern. We said that when we factored a difference of squares, it always worked out to be a conjugate product. I called it that at least once, but you may not remember that. Okay, so that goes both ways. If I multiply conjugates together, I'm going to get a difference of squares, right? Anytime I multiply the conjugates a plus b times a minus b, I get whatever the first term was squared minus whatever the second term was squared every time. So that's regular conjugates. Okay, now I'm going to separate that from the rest of the notes on this page, where we're going to talk about complex conjugates. So complex conjugates are almost the same, but instead of a plus or minus b, it's a plus or minus b I. Yeah, we're looking at two complex numbers that are conjugates of each other, right? So here we've got a plus bi and a minus bi. And as we're going to see, well, I don't know if we'll actually get to where we get to see this stuff, which is really just killing me this year. But there's a really strong connection between these two things. Okay, I'll just tell you what you're going to find. When we solve any kind of a polynomial equation, so polynomial just means like a I don't want to get too far ahead. Polynomial is just a sum of terms, and each term has a power of x. So a quadratic trinomial is really just a polynomial. It's got an x squared term, an x term, and a constant. Well, if we got one bigger than that, we'd say a cubic polynomial we'd add on the end of that, we'd add an x cubed term. And a quartic would add an x to the fourth term. So they just get bigger and bigger and bigger. If we solve any polynomial equations, what we find is that the highest power of x is what we call the degree in that polynomial. We're always going to have exactly that many complex solutions. Right? We guaranteed. Some of those could be real and some of those could be imaginary. What we find is that the imaginary ones always have to come in complex conjugate pairs every time. The solutions always come that way. They come in packets of two. I just bring that up just because it's related to what we're talking about now. But that's looking ahead a little bit. That's stuff we would have gotten to, in about, we still could get there. I don't know. It's debatable. It would have been stuff we would have gotten to maybe for us now, like in June. Question? No, okay. Okay, so what happens if we multiply together complex conjugates? Well, we're going to FOIL these out like normal. So now you guys tell me what's going to happen if I FOIL those out. Good. So those are going to cancel, right? And then finally, minus b squared I squared, which would be what? Minus b squared I squared would be the same thing as plus b squared, right? Because the I squared is going to make it negative, right? So those guys cancel, and look what we get. The product of complex conjugates equals a squared plus b squared instead of a squared minus b squared every time, okay? All right, that's useful to us because we can very easily multiply together complex conjugates then. What is this answer going to be? It's going to be something squared plus something squared. What squared plus what squared? H squared plus 1 squared, right? You see that? Give me thumbs up, thumbs down, thumbs sideways on that. Okay, good. All right. Because A is 8, and wouldn't you agree that B is 1, the coefficient of I? Okay, so that's giving us 65. How about this one? Just everybody, nobody say it out loud, but everybody just try to do that one in their head. What's the product of those complex conjugates? What'd you get? Did you get an answer, Elijah? for number 12.
Wait, I'm confused. Shouldn't it be 63? Because if the I is going to turn into a negative.
Okay, but look what happened here. When we multiplied out the complex conjugates, I got minus, really what this was a minus b squared I squared, right? I squared is -1, so it's going to make that a plus. So you always get, and let me put this on the notes page here. There it is right there. Look, the product of complex conjugates is always a squared plus b squared every time. So we got 8 squared plus 1 squared.
I thought the 1 was an I.
Oh, no. Yeah, the 1 is the coefficient of I. Okay? So what's this one going to be then? Say it again. Not 9, because it's got to be a squared plus b squared. Right? In this example up here, you guys tell me, for those complex conjugates, what's A? 5. What's B? 4, because I've got A minus BI times A plus BI, right? So then my answer is 5 squared plus 4 squared, not minus 4 squared, right? So I'm getting 25 plus 16, which is 41. So once you do a couple of those, you can do them in your head, right? I mean, just kind of got to get used to it a little bit. All right, so that's just a different kind of a product, a special kind of a product of complex numbers. Okay, now what about this? So when we're dividing complex numbers, we have a similar rule to what we had when we were dividing square roots. Remember, we had a no tent in the basement rule, right? Couldn't have radicals in the denominator. Well, similarly, when we're simplifying complex numbers, our answer needs to be in the form a plus b times I, right? That's our standard form of a complex number. So we cannot have i's in the denominator. That messes up the standard form. So what do you think we're going to do? It's really similar. What do you mean by that, Jack?
Like multiply the whole thing by I to get I out of the not I?
Okay, when you say the whole thing by I, do you mean the top and the bottom?
Yeah.
Exactly, that's right. Okay, we're going to multiply both the top and the bottom by I. And the reason for that is that's going to get the I out of the bottom, isn't it? Because what's 2I times I? 2I squared, so -2, okay? So I'm getting a -2 on the bottom, and on the top I'm getting a 10I, and we could simplify that. 10 over -2 is just -5, isn't it, right? So I'm getting -5I for my answer. Okay, how about number 14? What am I going to do? Actually, let's jump down. Let's do number 16. Yeah, let's look at number 16. What am I going to have? I've got an I on the bottom, so what am I going to do? Top and bottom by I. Okay. So what's that giving me on the bottom? -6. 6I squared. So I get -6. On the top, I'm just going to distribute the I, and what am I going to get? -8I plus 2, right? Minus 2I squared means plus 2, right? Okay, so now let's split that up into two different fractions. So I've got, I'm gonna write the top in standard form. So that's going to be 2 minus 8I divided by the common denominator, -6. But we want our answer to be in standard form, right? Standard form, remember, is the form a plus bi, right? And when I say a plus bi, it doesn't mean that b has to be positive. It just has to be the real part plus the imaginary part times I, okay? So then we could split this up into separate fractions. We could write this as 2 over -6 plus -8 over -6 times I.
Oh, you put I on the outside?
Say it again.
You want to put the I with the 8?
You could put the I with the 8. Okay, let's write it that way first. Either way is going to be correct. Let's write it that way initially, and then maybe we'll change it when we get things simplified. So then what's this going to look like? Well, 2 divided by -6, that's just the fraction -1/3, isn't it? Okay. -8 over -6 is the fraction 4/3. And now I'm going to split the I off and not put it in the numerator. You see why? Because this looks like, then it looks like A plus B times I, where A is equal to -1/3 and B is equal to +4/3. You guys see that? So when there is a fraction there, would it be wrong to put it in the denominator? No, but it's just clumsy. Right? We want to separate the I from that fraction just to really reinforce the idea that we've got some real number times I. Okay? Okay, so now when we're going to, that's the way we do it if we're dividing by a pure imaginary number, but it gets a little bit more complicated when on the bottom I don't just have a single I term, I've got a complex number with both a real and an imaginary part. So then what we do, it's a similar trick, but now to get rid of the I's, well, you tell me, what do you think you're going to do? What could I multiply? What would I need to multiply the bottom by there to get a real numbers with no I's? What do you think? I'm going to scroll up for a second. Look at numbers 11 and 12. Our answers are real. There's no I's. Drew, you got an idea?
We could multiply by the same equation, like opposite.
Okay, by the complex conjugate, right? When we take a product of complex conjugates, look, we get no I's, right? They disappeared. So that's the trick, right? We're going to multiply both the top and the bottom here by the complex conjugate of the bottom. Because the bottom is the one where we want the I's to go away, right? So what's that look like then? So we end up with 6 plus 4I divided by 4 minus 6I. And I'm going to put both of those in parentheses now because I've got to multiply those by another binomial, right? I got binomial meaning two terms. So I'm going to multiply each of those by the complex conjugate of the denominator, which is 4 plus 6I. And the nice thing about this is the bottom's easy. You guys tell me, what's the answer on the bottom? Take a second and think about it. What's it going to be? 52, right? Yeah. That's what everybody got? You get that, Elijah? On the bottom, 52. 4 squared plus 6 squared. 16 plus 36, 52. Right? Now on the top, we're going to have to do a little bit of just distribution, right? I mean, we're kind of stuck with that. So on the top, if we distribute the 6, we're going to get what? 24 plus 36I. If I distribute the 4I, I'm going to get plus 16I. And then what's that last term going to be? Elijah, what's that last term going to be? 4I times 6I.
24I squared.
So that makes it, there you go. Okay. So if we just combine the real parts, I get 24 minus 24. They go away, don't they? Right? So those are gone. I end up with 36I plus 16I. That's 52I, isn't it? So I get 52I over 52. So my answer is just I. Crazy. Okay? All right. We're out of here in a minute. Okay, good. So you guys are a day ahead. We'll come back and maybe look at one example next time, and then I'll let you work on this stuff. Okay?